Yes.
Yeah, you ready? Alright, so our next speaker is Madrid. Who's going to tell us about the connectedness of branch locus functions.
So, thank you, Gavino and Ernesto for inviting me. And I think the one has made all the calculations before was Ruben and Algo. So the talk is the opposite talk as some other talks. So what we want is to have non-maximum actions so that we can connect these. Right. And of course it's on the branch locus of the space and there's a group, so we have there are examples of Kleinian groups generated by losodromic. So if we have a Kleinian group, this is a discrete subgroup of P's to sit and sorry. So we have a domain of discontinuity on the sphere, and then if we do the Gaussian of the hyperbolic space and the domain of discontinuity by the Kleinian group, we have three manifold if with the possible boundary, and the boundary is a Riemann surface. And this is if we have no torsion, then we have a real manifold with the boundary a Riemann surface. And of course, if we have torsions, then we have orbifolds, hyperbolic orbifolds. So the group is it's a Kleinian group which is isomorphic to the free group of branch H, G, and it means that they have only losodromic elements like this. And we have seen they a number of times already, and this is for instance, masked the construction. You take 2G neutral and disjoint circles, and you take losodromic elements that map one sample to the other in such a way that the unit disk is mapped. So the domain is there, and then we get a handle body, and with the boundary of the handle body, because we wanted to have non-empty region of discontinuity, a Riemann surface of genus G. So this is we call also the shorty groups will have the genus G, and this is a group of genus 3. And now this morning we have talked also about the quasi-deformations and quasi-conformal deformations. So now we have a market, a lot of market group. So we have a Soki group, and we have a market that is we are given exactly the circles. So we have the length of the circles, and of course the length of the circles they will give us a marking on the fundamental polyhedron for the handle body, and also for the fundamental polygon of the corresponding Riemann surface in the boundary, right? So this is that there. So you see, we are talking about the Teichmüller space here. So when we have the handle body with the marking Kleinian structure is to have the gamma with the market circuit structure. So we are saying how are the generators, and of course automatically we get also a market hyperbolic structures for the Riemann surface in the boundary. So we are living in the Teichmüller space of Riemann surfaces. And of course now if we have the generators, of course if we have a market, if we want two Soki group markets, Soki groups to be equivalent, we have to have a Möbius transformation such a way that the generators of the one are conjugate to the generators of the other. Right? So this is the same, in fact, that talking about the Taylor space in the of the Hamel body, which is a part of the Taylor space for the surface, because the generators will give us the surface, and Bears show that in fact the Taylor space is a quasi-deformation, so it's the Taylor space, so that is part of the Taylor space of Fuchsian groups. And of course, we are interested in conformal things, not in geometry, but in conformal structures. So what is what we do? We forget the marking. And now we said, well, two Kleinian structures on a Handel body, or two Schottky groups, are conformally equivalent if there is a diffeomorphism of the Handel bodies in such a way that there is a conformal homeomorphism, so it's the Riemann surface are conformal. And of course, the interior of the Handel body lives in dimension 3, so even I said I forget the symmetry, but in dimension 3 we have rigidity, so if I said that I have an homeomorphism and it keeps the structure of the cranium, and I said I have an isometry, it's the same. This is why I'm putting isometry, we have rigidity. And of course now we consider the space of Schottky structure, so we don't have any more marking, and we correct. And of course now is if there has to be that we have the two Schottky groups, they have to be conjugate by Möbius transformations. But notice that the generators don't need to be conjugate. So we are completely forgetting the marking. This is the difference. And of course, we said that it was part of the Teichmüller, so we just consider the part. The assume, in fact, the assume by the automorphisms, the outer automorphisms of that. And this is part of the Teichmüller, so it's something of complex dimension 3D minus 1. And by the way, I always, when I write 3 times d minus 1, I'm always thinking about the complex dimensions. And it's very important. We have the Teichmüller here, and we have the moduli space of Riemann surfaces here. The Schottky space is intermediate covering, which in fact is non-regular order covering, because this is an order for. It's a cosine of something that lives in the Teichmüller, so it's an order for. And well, this is again to say how we go from the Teichmüller space for Schottky groups to the Schottky space. What we have in fact is the cosine by the outer automorphism of the fundamental group, which is the Schottky groups, which is the free group of range G. And of course we have this universal covering, and as always in orbifolds we have the branch locus, which is the one where we have branches, and this has happened for Riemann surfaces. Also the branch locus is given by those Schottky structures on the Handel body that admits non-trivial automorphisms. It's only that for Riemann surfaces, for genus 2, we have always the hyperelliptic involution, so we have to take away the hyperelliptic involution. So we usually say for genus at least 3, or automorphism is different from trivial and the hyperelliptic involution in genus 2, and here we can put genus 2, and of course I'm always thinking hyperbolic structure, so the genus is at least 2. And well, The difference from the branch locus for Riemann surfaces is that there is very, very disconnected. Here, if we are the branch locus for the Schottky space is connected, the genus is these three, and it has exactly two components. If the genus is two. And this is just to show that. So if we are talking about the Riemann surfaces, the branch locus is very, very disconnected. But if we are talking about the Schottky space, the branch is, which means that it is connected, that the genus is at least three. It means one thing, that the branch locus here maps, it has to be connected, maps on one of the connected components of the branch locus of the Riemann surfaces, of the modular space. And in fact, we know which, then you will realize when I show the morality of the theorem, that in fact it has to map on the branch locus containing automorphisms which are involutions, so the surfaces that are mixed involutions. And the thing is there are somehow more Riemann surfaces admitting automorphisms that the ones that admit automorphisms that can be extended to a Handel world. So not all Riemann surfaces with automorphisms are boundaries on Handel worlds. That's the morality of the thing. And and of course this was Ruben that did it, and you will find many. So now as that there, so we will decompose in the branch locus in families which are good enough. And the families of the branch locus have to be automorphic. They will be what we call cyclic sorted group. So they are given by an automorphic. And of course we extend the Schottky groups with this with the subgroup generated by this automorphic. And it's also one can show that in fact the order of this automorphism could be taken prime. So these families, they will be families of Kleinian groups which are extensions by a prime order cyclic group of the Schottky group, which is the fundamental group of the Handel body. And first we have to show that there are not many of such families that are connected spaces, right? And they will be, I will tell you already, because it's sad that these families are given by the automorphism of the Riemann surface or the Handel body is involutions. And then we have to find that we can connect these families, which will be given by involutions, to whatever other family given by automorphisms of prime order, right? And well, then, but these families, somehow we have to connect everything with everything. So first we will connect these families with whatever is the order of the automorphisms to families given by involutions, and then we have to see that we can connect involutions. So what we are trying to get is we have two Kleinian groups, which are cyclic groups, K1 and K2, and we have an extension of them, right? That contains them. So the opposite as given maximal, as we want maximum which are not maximal, so we can always extend. Okay, so again, now it is topologically, if we want a cyclic group, so we need these automorphisms of prime order, I said, of the Handel body, which also induce the automorphisms of prime order of the of the Riemann surface, which is the boundary. And well, of course, we take now, if we cut by the automorphism, if we take this handle body cut by the automorphisms, we have an orbifold, because we have the branching, right? And it's also, we have also an orbifold, by the way, in the boundary, right? And of course, we can always say what is, how is the monodromy we have there. Of course, the monodromy is present the Kleiner group, the cyclic Schottky group, to the subgroup generated, or the group generated, the cyclic group generated by the automorphisms. We also know what is the algebraic structure of this cyclic Schottky groups with P is a prime. We have T losodromic, because well, of course we have to have the losodromic there. Then we have R elliptic elements, which are of course the P given by the automorphism, right? And we have also the combination of the losodromic and an elliptic and the rotation, because we can have the. So this is, and then we will say that this is of type G, because it's acting, because the subgroup, the Schottky subgroup, the normal is of index P has range G. P is the order of the automorphisms of the Riemann surface. P is the losodromic generators, are the elliptic generators. S is the combination of losodromic and elliptic elements. And this is everything right. And now we can in fact find in geometry just by doing this with it, length of arc. So with geometrically, this the action of the automorphisms of order P on the handle body, we have fixed points, and it will be of R simple arcs, which give us 2R cone points on the boundary, on the Riemann surface, which is on the boundary. So remember, this R will give us 2R cone points on the boundary, and it will have also S simple loop every time we have the rotation, and losodromic send us to the simple loop. And the orbifold quotient will have topological genus. The genus we have already with the T losodromic and the S. The genus will be given. The genus will be given by the losodromic elements. So we have here T and we have here S. And of course, I told you that the boundary, the orbifold in the boundary will have 2R cone points, that all then has to be of order P, because P was prime, and the gamma we calculated with the Riemann Hurwitz formula. As a consequence, any two cyclic Schottky groups at the same time will be quasi-conformally conjugate. Quasi-conformally conjugate. They won't be, in general, conformally conjugate. I told you because, well, this is an example of a cyclic group. In fact, one is not. I have said 3, but doesn't need to be 3. It has a losodromic generator. It has an elliptic generator, and it has the combination of losodromic and elliptic generator. Well, and now what the theory, which is the algorithm. as I have told you the algorithm. So we consider the subsets, the families of given by the cyclistic groups of genus G, admitting an involution of order P prime, the T, nosotropic generator, the R, okay? And of course they are that, and doing the calculation for the genus minus 1 has to be P times the T plus R plus S minus 1 minus and of course we have, and now we know that because we are talking about the the branch locus is in fact these families are subfamilies in the branch locus, just because it has the involution. Now, very important, I'm not saying that, I said they are quasi-conformally equivalent, and I didn't say anything about conformally equivalent and that, and these families can be disconnected. And in fact, if P is at least 5, and R of S is not a multiple of the prime, they will be disconnected. For genus at least 6. So this we know this disconnected. In genus 2, these two families are disjoint, and any other of the groups that they can appear in genus 2 either intersect this family or intersect this family, but they never intersect both families at the same time. So in genus 2 we have is disconnected, the branch locus. And except if there are involutions in for genus at least 3, the involution they are called Whittaker groups, and Raquel with Rubens, Gregos, and Ignacio, they prove that these families are connected, the ones given by involution. So they are, and then we could prove that if any other family, whatever is in the connected component, it will always intersect one of these families given by the involutions, and I have here. This is because whatever is the family, this is, for instance, something which is trigonal. The P is equal to 3, and we can always find this involution. So you have this involution, then you extend your cyclic sorted groups with the automorphisms given by the involution, and then you have a super triangular group containing both of them, so you are putting all them together. And then what is happens, so now the only thing you have to study is these families given by involution. And if you see, if for all genus, it only depends, in fact, it only depends if the T is even or odd. And so it's either, if any of this family will cut this family 1 or this family 2, depending on if the T is even or the T is odd, in fact. But this family, we can find that in fact they cut each other, so we are getting a connection. And if the G is even, at least 4 because the 2 that there, this family will cut any of these 1, 2, 3, 4 families. If it is the T and S are both even, the T is odd, the is even, and here is the T is even, the S is odd, and here is both of them are odd. And then we can connect every time both every time the t is even, we can connect them. It's easy fine. Or every time the s has the same parity, the t is, or we can connect them. And of course we have we still have to connect the component, but it appears here one which is called, which has both the, we call it the elliptic Whittaker group because it has no losodromic part, and it this in fact cuts the other two families, so it gets connected. And this is the intersection of the hyperelliptic locus with well, Aaron, they have the examples of maximal Hessians getting the disconnection. Thank you.
Any questions?
Is there like some graph or something that describes the way all of these dimensional sides intersect each other?
Not yet. Well, there is a graph for the families G, P, it's at least 5, T, R, S. There is a graph there. We thought no, because I mean, we are not looking for possible fields. As soon as we find an example of a Kleinian group, done. I mean, for instance, we don't know if there could be other with P different of 2, that or 2 different P's, not 2, that also we don't know, we are not. So I think it's much more complicated that